Hi everyone, this is Lingzhi from Nanjing University. Today I am going to talk about the specification and verification of distributed systems and share our practice and experience on writing multi-grain specifications for distributed systems to address the challenge of model code gaps and state space explosion. This is a joint work with my fellow students and our advisors from Nanjing University and University of Illinois. Nowadays, many distributed systems are built upon sophisticated protocols and implemented with complex mechanisms to meet a variety of requirements in the face of non-deterministic workloads and failures. This inherent complexity makes them error-prone and difficult to develop and maintain. Consequently, formal methods have been increasingly used to verify not only the protocol, but also systems code. In recent years, formal methods start to go beyond academic research towards verifying production distributed systems. For example, companies like Amazon, Microsoft, MongoDB, and LinkedIn all use formal methods to specify and model check production systems. Among these work, TLA is a widely used formal specification language for verification. In this work, we focus on the verification of Zookeeper, a complex, widely used coordination infrastructure by a variety of distributed systems, which rely on Zookeeper to store service metadata and perform essential coordination tasks. Therefore, Zookeeper's reliability is of critical importance. However, as Zookeeper evolves these years, we observe that deep critical bugs are still be found in implementation. Some of them remain unresolved for a long time or fixed without sufficient verification. Here show some bugs originated from the optimizations in 2017. Among them, the code phase of the issue 3911 was buggy and lack of sufficient verification, and it introduced more subtle bugs in latent versions of Zookeeper. Zookeeper developers lack efficient techniques for bug detection and fix verification. We resort to formal methods to improve the reliability of Zookeeper. Actually, before this work, there exist two official TLA specifications for Zookeeper, the protocol spec and the system spec. The protocol spec follows the pen and paper description of the original ZAP protocol from the ZAP paper, and the system spec is developed based on the Zookeeper source code. Since our goal is to verify the implementation, we start with the system spec. The system spec is a concise system design document for Zookeeper development. This figure shows how the code implementation of Zookeeper is corresponding to the system code. The code snippet on the left is about a follower's processing logic upon receiving a target message, and it is translated into an atomic action in the TLA spec. However, there is a fundamental challenge when using this spec to verify the implementation, the model code gaps. That is, the spec does not effectively reflect code-level implementation. For example, Zookeeper's code-level execution does not guarantee the atomicity of the actions labeled 1 and 2. However, in the spec, the state transitions from 1 to 2 to 3 are always atomically done, and they are specified in an atomic action. In this case, if the actions 1 and 2 are partially executed and then interrupted, the intermediate states will be missed in model checking. It is common that coarse-grained spec introduce model code gaps easily. Consequently, verifying or model checking cannot capture subtle bugs whose manifestations are abstracted away from the model. We observe three common types of model code gaps that often induce tricky and error-prone implementation: atomicity, concurrency, and missing state transitions. We find that model code gaps are prevalent. One main reason is that implementations are highly optimized, and the optimizations are rarely modeled in existing specifications. Intuitively, we could further model important fine-grained behavior like non-atomic updates and multi-threading concurrency for verifying code implementation. However, doing so would significantly increase state space, resulting in state space explosion. Currently, using the TOA model checker to verify the system spec of Zookeeper can finish in 10 days with a standard configuration. So here comes the dilemma: how to balance the scalability of model checking and the granularity of specifications in modeling code-level implementation. To address this challenge, we write multi-grain specifications, which are multiple specifications with different granularities for composable modules, and compose them into mixed-grain specifications for specific scenarios. The fine-grained modeling reconciles specifications and code implementation, and the coarse-grained modeling reduces state space, and it avoids state space explosion. We developed Remix, a framework for model checking and verification of distributed systems with multi-grain specifications. It composes module specifications into mixed-grain specifications and provides conformance checking to preclude deviations that could be introduced when writing specifications. Using Remix, we have detected 6 debugs in Zookeeper, verified their fixes, and improved the protocol design. Specifically, we write multi-grain specifications based on an existing spec. To code with model code gaps, we do fine-grain modeling to obtain the spec that conforms closely to the code. Besides, we do coarse-grain modeling to reduce the state space. Then, we can obtain the mixed-grain specification that consists of fine-grain specs of target modules to model code-level behavior, and coarse-grain specs of other modules to save cost. For example, when verifying module C, we compose the fine-grain spec in module C and coarse-grain spec of other modules into a mixed-grain spec. Mixed-grain specs enables us to verify the system module by module and to verify code changes or bug fixes quickly. How is the fine-grain modeling conducted? We propose some principles for the 3 common patterns of model code gaps, which are detailed in the paper. Here presents an example for non-atomic updates. For an action that is not guaranteed to be atomically executed at the code level, but specified in an atomic action, we need to rewrite it in the spec by splitting the action into multiple separate actions and set up their enabling conditions accordingly. We design atomic blocks based on how threads or nodes communicate. An atomic block starts with reading the external state, performing internal computations, and ends with writing to the external state. Besides, we do coarse-grain modeling of non-target modules to reduce state space. To ensure verification safety, the coarsening must follow the interaction preserving principle. Simply speaking, we distinguish 2 types of variables in each module in the spec: the internal variables and the interacting variables. For a coarser module, only the internal parts can be omitted, while the interaction with target modules must be preserved, such that the target modules cannot distinguish whether it is interacting with the original or the coarsened one. For more details of the formal definition and the proof, please refer to our paper. With the fine-grain modeling and coarse-grain modeling of different models, we can easily compose them into a mixed-grain spec. So how to ensure the spec quality? In practice, we do conformance checking to ensure that the specs we wrote match the implementation. Here is the workflow. First, for a spec, the conformance checker explores model-level state space randomly to generate model-level traces. Then, it replaces them in the implementation to generate code-level traces, and compares model and code-level traces. If the conformance checker detects a discrepancy between the spec and the implementation, we debug and revise the spec to match the code behavior. After the spec is updated, we run a new round of conformance checking until it passes. The continuous conformance checking helps us find several discrepancies and improve spec quality efficiently. We wrote Ruize as a framework and tooling support for composing mixed-grain specs, interfacing the model checker, and providing conformance checking. The workflow is shown here. First, we select the spec of each module and compose them into a mixed-grain spec for the entire system. Then, we run continuous conformance checking to ensure the spec is synchronized with the implementation. After obtaining the high-quality spec, we model check against the spec and check if any safety violations is occurred. To avoid false alarm that caused by discrepancies, Ruize replaced each module-level trace that violates some safety property to confirm that the violation also happens in the code implementation. Ruize realizes deterministic execution by having a central coordinator that intercepts and coordinates actions from different threads on different nodes. The coordinator takes a module-level trace as the input, schedules the code-level actions one by one according to the module-level trace, and ingests faults when needed. In practice, we have written multiple specs with different granularities for different modules based on the system spec of Zookeeper. So how is the effort of writing multi-grain specs? Actually, they can be obtained incrementally. Most variables and actions in the baseline spec are directly reused. The effort is done within 40% hours and is done by a person who is familiar with the Zookeeper code. Overall, the efforts of writing multi-grain specs are manageable, and the cost can be amortized as more specs are written. We specify 14 invariants that are checked throughout the model checking. 10 of them are safety properties defined by the Z protocol, and other 4 types are derived from the code, such as the assertions from the code. Using these mixed-grain specs, we detected 6 debugs in the latest version of Zookeeper at that time, including 2 known bugs and 4 new bugs. Some of them violate code-level invariants, and others violate protocol-level invariants. The triggering parts of these bugs all require more than 10 steps. As Zookeeper developers provide multiple code fixes for these bugs in their pull requests, we use the mixed-grain specifications to verify the code fixes and discover that all of them violate some safety properties within 5 minutes. As for the verification efficiency, we have conducted 2 experiments. In the first experiment, the model checker starts when it detects the first violation. In the second experiment, the model checker starts until it detects 10,000 traces with safety violations. Both experiments show that mixed-grain specs with fine-grain modeling and coarsening can finish or detect violations in tens of minutes. However, the system spec cannot finish or detect violations within the time limit. And the fine-grain spec without any coarsening costs much more time to detect the first violation. So mixed-grain specifications effectively improve efficiency of verifying the target modules. We also found that as Zookeeper evolves these years, the Z implementation deviates from its original protocol design. For example, an atomic action in the protocol is not faithfully implemented in the code, which optimizes the performance without correctness guarantee. Based on this observation, we improved the original protocol for better performance and used the mixed-grain specs to verify the correctness of the new protocol. Based on the improved protocol, we further provide code fixes for all of the detected bugs, and again, use the mixed-grain specs to verify their correctness. At last, our approach helps fix all the detected and long-lasting issues presented here with efficient verification. Here's the summary of the results. The manual efforts are reasonable, and misgrant bets are effective and efficient in bug detection, face verification, and protocol improvement. Actually, this approach is applicable to other distributed protocols and systems, as model code gaps are common, and interaction preserving principle is a general principle applicable to other specs. Besides, phase-based modularization is common in distributed system design and implementation, which simplifies the verification module by module. As for the soundness and completeness, this approach could miss behaviors in implementation that are not modeled by the spec. However, it guarantees no false alarms, as we conduct deterministic replay of the chases with safety violations. For the maintenance of the specs, as most code changes are local, most modules and high-level specs stay unchanged, and the misgrain specs can make continuous verification more efficient. In conclusion, writing multi-grain specs and composing them into misgrain specs is a viable practice to code with the model code gaps and manage the state space. We open source the Ruize framework and our multi-grain specs online. Thanks for listening, and this concludes my talk. Thank you.